Welcome to Web Handling. My name is Dave Roysum. I am very excited to begin a new mini-series on framework design and troubleshooting. The framework is the skeleton that holds our machine parts together. It is as essential to good web handling as our bones are to our body. Yet, in spite of its importance, framework has gotten almost no mention in the literature. We will try and remedy this in a small way here with this series. We begin with the foundation that underlies all of our frames. Machine designers evolve. The first hurdle is to learn how to build a frame and foundation strong enough so that they don't break. This is true in most cases as the marketplace weeds out the weak rather quickly. The next hurdle is to make the frame stiff enough so that it doesn't bend. We covered this requirement in great detail in our Web 101 class. Briefly, the bending under full load must be less than roller alignment tolerances, which are on the order of 1 hair's thickness for most machines. This would be about 125 microns in the metric system, or about 5/1000ths of an inch in the US system. However, not allowing the frame to bend more than, say, a hair's thickness may not be nearly good enough for heavy or high-speed machinery. Here, a dynamic movement of a hair's thickness in a key location, such as at the foundation, would make your teeth chatter elsewhere. You might even be reluctant to get too close for fear that something might fly apart. There is one other consideration that is important for all but the very smallest of machines. That is, foundation movement can cause long-term maintenance troubles in keeping rollers in alignment. As foundations settle, the rollers can be twisted out of alignment. As framework creeps, rollers can be twisted out of alignment. One criteria that has been way overstated is critical speed. For all intents and purposes, simple roller critical speed calculations are not only meaningless, they are non-conservative. Meaningless because they don't consider framework compliance that reduces actual critical speeds. Non-conservative because you overestimate the critical speed. Being non-conservative means that you pay more and you get less than what you think. The truth is more complex. There are an infinite number of system resonances, even though the lowest frequencies tend to be the most problematic. The truth is more complex because there are an infinite number of forcing function frequencies when a wound roll is involved. Still, the bottom line is simple. Resonance is inevitable at higher speeds, so don't worry about it. The bottom line is usually simple. Build machines stiff enough for deflection purposes to hold roller alignment, and you'll generally have a vibration-resistant frame. Then, one more critical step. Balance or superbalance the rollers. For those who want a brief peek at vibration complexity, I offer the following mode-shape diagram of the simplest machine possible. That is, a roller on a flexible frame supported by an infinitely stiff foundation. Here we see that mode 1, where the roller and frame bend together, is the lowest and almost certainly the most troublesome. Yet it is mode 2, a higher and less interesting mode, that is approximately calculated by simple formulas. There are an infinite number of more complex modes beyond these, and they involve intermediate nodes. Of course, real machines are far more complicated than this diagram, and do not lend themselves to anything like a simple and relevant critical speed calculation. Also, foundations are flexible, as we'll see in the next slide. You must use finite element modeling or vibration analysis to proceed any further, something I spent a couple of years on when I was a young designer. Foundations can shear, especially if they're on the second floor and have expansion joints. This can be minimized by driving wedges between the sections, though that defeats the purposes of the expansion joints. Foundations can bend, especially if they're on the second floor and the machine is between columns. This can be quite easily be minimized by driving a vertical jack post under the machine. Foundations can twist, especially if they're on the second floor. Only stiff sill beams or continuous walls underneath the base plates can solve that problem. This material is thoroughly covered in a 1988 Tappy Journal article as well as in an upcoming Web201 clip. Still, as seen in the next slide, even first-floor foundations must consider many design and maintenance challenges. For very small machines, say desktop size to very narrow converting, foundations might be quite simple. Perhaps just setting on a conventional 4-inch thick office or 6-inch thick plant floor slab may be enough. Still, I would like you to consider a 3-point instead of a conventional 4-point mounting leg. This tripod will conform to any floor shape without internally twisting the frame. For more typical converting sized machines, we need to do quite a bit more. We begin by ending the excavation on undisturbed earth. Upon that, we place a foot of gravel that helps isolate the near inevitable movement of the earth from the concrete slab above it. Finally, instead of mounting the machine directly to the slab, we might consider mounting the frame onto base plates or a pair of base frame rails that are epoxy grouted into a concrete rail. A pair of concrete rails of perhaps a foot by foot cross section is quite easy to construct if you think ahead. These rails help preserve internal relative alignment of your machine in spite of the near inevitable movement of the slab. For rubber, paper, steel, and other heavier high-speed equipment, we may need to do quite a bit more. Here, we may need to mount directly on 1 meter thick walls extending well down into the earth. Here, we may simply spend $100,000 on concrete instead of doing a $100,000 finite element study to determine how much concrete is actually necessary. In any case, for all but the smallest machines, it is stability rather than mere load carrying capacity that is the usual limiting factor. Still, despite these best practices, we can have long-term maintenance challenges related to the foundation. All you have to do is look at your aging floor. If you see any cracks, you can conclude that foundation movement is already far beyond roller alignment tolerances. This is because, with the exception of bedrock or caliche, most soils act like viscous liquids. They expand and contract with seasonal changes in moisture. Worse yet, some buildings must be floated on large pylons driven into the earth because there is nothing but muck for more than 100 feet beneath the floor. Indeed, plants near the coast or coastal waterways may even move with the tides. So, how do we deal with the movement of the earth beneath that is almost inevitable with most plants? Simple. Build on concrete rails or steel base frames that tend to preserve internal alignments of the machine above. These are very inexpensive if you think ahead when doing site planning and civil engineering. Thank you so very much for watching this module in my Plant Practical video series. Stay tuned for the next clip where we will continue our discussion of best practices design and maintenance of web machine frames. Be sure to like and share. See you next time.